They're not totally useless. Okay, so we're on air. Hello, YouTube. I want to show the whole desktop. That's fine. Right. So now, don't bother me. That's the important thing. We've done that. Let's go to. Never mind. I can find it. Let's go to our slides. Let's open that. Okay. And let's open. Never mind. Oh, this took a long time. So on Wednesday, we started talking about the kind of problems we want to solve. And we're just doing problem solving at the moment. And it'll certainly slowly merge into real computer science. Well, this is the real computer science. Computer science is not learning a particular language really, really well. It's knowing the concept, the way of thinking. How do I analyze a problem? Where do I start? That is the real core of programming. If you can do that, you can solve any problem in any language. If you can't do that, you can't solve any problem in any language. So, well, actually, we stopped here and we were talking about how to generalize problems. And I was trying to show you examples. But you have to keep up with the other class, and they go really fast. They don't tell stories like I do and babble and talk about my weekend and all kinds of stuff. So let's speed up a little bit. We could work through all of these questions, and if we have time, we shall. But you're not idiots. I mean, you guys passed the trick. Most of you can read and write, and I mean, you're clever guys. So you'll read that and you'll find out. How do we write these programs? These not programs. How do we write the algorithms? How do we write the solutions we come up with for different programs? I mean, we have to write them down somehow, and we've got many, many choices. You can use a natural language, so just follow. Step 1, blah, blah. Step 2, blah, blah. Step 3, blah, blah. Unfortunately, English has problems. It's very ambiguous. You might think it's clear, and you might think when you speak it's very, very clear, but especially when you write technical stuff, it takes an extreme effort to be absolutely accurate when you express language. So most people can't write that well, or don't want to write that well. It takes a lot of effort to write very clearly in English. You think it doesn't, but I promise you it's terrible. We can use something called flowcharts. So a flowchart is a little diagram that shows you the steps. And basically, it's English in boxes. I draw a little box, and I write an English description of what I do, and then I draw an arrow, and there's another little box, and then I draw an arrow to the third box. These are all my different steps. And sometimes I have to make choices. Do I do step 3 or 4 first? And then these flowcharts will have 2 arrows going out of the box, and you can make a choice. So it's like a little diagram of your thought process. And that's fine, and it's used a lot. And in fact, you don't have to put English in the little boxes. You can put something else in the boxes. One of the 2 bottom approaches. What we'll be using, at least for now, is pseudocode. So pseudocode is a mix of English. There are no rules. I can really write what I want. But also a programming language. So I can't really write exactly what I want. There are some restrictions on what I can write down, what qualifies as pseudocode. But the bottom line is really that when you write pseudocode, you're really writing an algorithm or even a computer program, but you're not constrained by a specific programming language. When we get to the last step of programming language, programming languages were designed to make it easier to program a computer. Long ago, in the 1940s, even in the 50s, if you wanted to program a computer, you have to speak the computer's language in a very literal sense. So the computer had some list of instructions, maybe 200 different, very strange instructions, and you have to feed them to the computer in the order you want them to be executed. And every time you feed them, you have to toggle a lot of switches to specify which instruction you want, and then press a button and enter the next instruction, and so on. So people got tired of doing this. There were lots of mistakes made. So they developed programming languages where you can write in something that's a little closer to English, something that humans can understand easily. And in fact, we write programs for other people. The computer really wants that binary, the digits, the instructions. That's what the computer really wants. Using a programming language is actually inconvenient for the computer because it needs an extra step of translating what you've written in a programming language to something the computer understands. We write the programming languages for ourselves and for other humans because it's easier to communicate like that, but it's also very precise. So programming languages have strict rules. This whole course is about learning those rules for one language. The rules are pretty similar from one language to another, so it's pretty easy to learn a new language. But you have to know the rules, and you have to stick to them. And this is just the mechanics of programming. The real thing you have to learn for programming is thinking in a certain way. But it doesn't help just thinking. We do need to express what we think. We do need to communicate the solution we find to a computer. So we do need something. As I said, we'll be using pseudocode. We won't even go near it today. But I'll remind you of this just so we know. One of the conditions of pseudocode is you can't just say anything. You can't tell the computer things like solve the problem. If that was available, that's how we solve all problems with a computer. There would be no jobs for programmers because the only programmers will solve the problem. So that's a little too high level. We have to give the computer instructions. We have to think of our solutions in smaller steps. And we only have a few steps to choose from. In fact, we only have these 5 steps that we can use. All the algorithms we design, all the problems we solve, the jar problem, did I show you in the other problem? Maybe not. Let's take the jar problem because it's nice and easy to understand. You've got those jars, they've got different capacities, 9, 7, 11, I don't know. And you want to measure a certain volume in a jar. To solve that problem, I have to break it down, I have to solve it, I have to break it down into steps, and these are the possible steps. I can acquire some data. That's probably something I want to do first, because I want to be able to acquire the parameters of my problem. So what are the jar sizes? So acquire data is one kind of step I can take in these programs or solutions that I write. I can do some kind of computation, like fill one jar with as much of the contents of the different jars as you can. So that's a kind of computation. I'm changing the state of things. I can do selection. In this context, selection means making a choice. I can say something like, if this jar is less than half full, or it contains 1 liter, then do the following step. But if that is not true, do something else. So I can make these choices. You can imagine that the can't just write programs to this computation, computation, computation. Well, it's fine if you have to calculate the volume of the box. The only thing for the volume of the box is acquire the data, get the dimensions, multiply the 3 dimensions together, and then the very last step, report the results. It's only 3 steps to solve the volume of the box problem. But the jars is more difficult. You can't just have a linear list of steps. I probably have to I have to be able to make decisions now and then. And the missing one is iteration, repetition in other words. To iterate means to repeat. And well, now I'll tell you Afrikaans for this stuff. Acquire data. Toevoer is input. Computation is berekenen. Selection is selectie. Iteration is iteratie. Report results is report resultatie. output our food. Okay. Iteration is the missing one, which means to repeat. Sometimes, I mean, if I want the computer to do some step, like filling a jar 20 times in a row, I can write my solution and repeat the step 20 times. But that's really wasteful. So I'd rather say something like in iteration, repeat the following steps 20 times. The following steps is simply some kind of computation like empty a jar, fill a jar, or what have you. So this will be our language. Not today, but tomorrow, on Monday we'll start writing little programs using this kind of language. It's not precise, there are no rules. I'm just going to check up on you. I'm just going to say it's wrong to write in a certain way. On the other hand, there is a kind of feeling that, whoa, that step is pretty high level. You can't just say, find the volume of the box. You have to explain a little more how to do that. Right here. We call this pseudocode. On Wednesday's slides, there was a problem that we, of course, never saw because I go so slow, about cutting a chocolate bar. And after Wednesday's class, somebody told me that they found the solution for the jar problem, which I'll admit, I don't know, I just plucked it out of. It occurs a million times in textbooks. So I couldn't tell them if they're right or wrong. But if this class is really too boring, here's another problem that we'll get to on Monday. This problem says you have a chocolate bar that's divided into squares. As we all know, all chocolate bars are. It's got these grooves, so you can cut it or break it. Usually you shouldn't break it because it always ends up breaking in a funny place. And then you have to eat the extra piece of chocolate. Oh man, it's such a curve. So it's got these grooves, so you can cut it. There's a rule here. That is that if you cut the chocolate bar, you have to pick up a piece, doesn't matter how big it is, make one cut along the groove. You can't stack them all together like one big cut. Given that rule, how many cuts do you need to break the chocolate up into all its individual squares? Now, obviously, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. There are 32 little squares in this bar of chocolate. So, if I want to break the bar up into the 32 squares, one thing I could do is cut along every horizontal groove and cut along every vertical groove. That would be 7 and 3, that means 10 cuts. No. Am I making a mistake? It's so difficult. If I cut it horizontally and I get 8 separate pieces, I can't just make one long vertical cut along a groove that goes that way. Sorry, YouTube. I can't just cut along that groove because I now have 10 pieces. So I have to take 8 pieces. I have to take each of those 8 pieces and cut its groove individually. And that would be 8 times 3, which is 24, plus the original 7, which is 31. That's a lot of cuts. So the puzzle is there a way to use fewer cuts to break the chocolate into smaller pieces? Should I cut along the long vertical grooves first and then cut up to the individual? Should I halve? Should I go like, break it into, try to break it? Why don't you meditate on that during the weekend? We'll talk about it on Monday. But what we really need to talk about today is something else. We need to talk about Kevin. No, we need to talk about something. Oh, these 4 ways of solving problems. So we said that that's this 4-step approach, which we only saw the first two steps of, which said the first step was understand the problem. So ask questions about what does the inputs mean, what is the only inputs, is the problem satisfiable, is it inconsistent somewhere or not. And the next step of the 4-step approach was thinking of a solution. There were many suggestions, but I said one of the set of suggestions is that you use a technique. If you know different techniques, whatever that may be, They apply to many, many different problems, and they'll help you solve the problems. So we're going to look at these 4, and today we'll start by looking at induction. Who knows what mathematical induction is? Why? Why do you know? Where's Aiden? What happened to Aiden? He's quit. No, not you. Are you Aiden?
No, I'm me. Hi.
Very good. Is that Aiden? Who? And you went pretty close too, I see. Where's Jason? That's it. Oh, Jason. You also moved. And who was my other victim? Robin. Okay, Robin's also moved. Okay, let's just pick new victims. Right? What? Always. Owen. Okay. Why is it bring this hard name? Owen. What does that mean? What is I'm sorry.
RW114
I'm sorry. I know. Owen, yes, that's what I said. What does it mean? You don't know what your own name means? That's terrible. That's like Robin, nothing as a Robin. Oh, okay. That's like the you know what it is? Do you know what it is? Trevor? Jamie? Kevin? What? Okay, right. You admitted that you know what induction is. You admitted you knew. Name? Florio.
like Mario.
Florio. I mean, you can't get out. I'm going to get out. See. Like he's having me. Okay. Okay, I'll just go with Rico. Right, what does the Rico mean? Very clever. You speak Spanish. How about you?
I don't speak Spanish. I don't speak anything.
I happen to know the answer. Actually, I don't think that's what the Rico. What do you mean? Torah is called, Torah means development deer. And Lolita means my little deer. Anyways, giving back to the problem at hand, but not to production. Original. It sounds like no useless. Yes. Okay, right. So I suspect it as Dorian just told me that it's in the AP tracks. Okay. So what about the people who didn't learn about it? Isn't there a little bit of induction to school maths? That sucks. Never mind. You'll find out soon enough what it is. It's so simple. Even a child. Right. Now, where did I put it? Never mind. So, we're going to learn about induction and we're going to apply it to problems. Now, you'll see a problem. You won't know how to solve it. You'll ask all those questions on the list in the step 1. Do I understand it properly? Then you'll move on to the questions in step 2 about how am I going to solve it. One thing you're going to ask yourself is, have I seen this kind of problem before? And maybe you recognize it and you remember that I solved it with induction. And nobody remembers the catalog of all the problems I've seen before, but you get a feel for it later on. Just like when you hear music on the radio, Mario, when you hear some kind of Italian artist, who's an Italian artist you know? Yeah, what about Cheyenne? Is he Italian? No, maybe Latin. Let's say you listen to your favorite legend of Silvio Berlusconi. Or the Pope, who produced the hip hop album. Yes, you're listening to the Pope, Mario. You don't know all the songs in history. Okay. So, but you still recognize songs you've heard before. And it's not as if you give him catalog, you see it so often, you hear the songs often, that you build up an internal model or internal list of problems you've seen before. So, maybe you haven't seen the one before, it doesn't remind you of something you solved with induction. And then you can still tell yourself, okay, I don't know how to solve this problem. Which techniques do I know? I know induction. Can it apply to this problem or not? Can I find a way to use induction to solve this problem? And if it doesn't work, it's fine. We move on to the next technique. But sometimes it does apply, and then we try and see if we can solve it. Here's our problem. A number of straight lines are drawn on a piece of paper. So they're straight. You go from one side to the other side. The paper is now divided into little regions. And the question is it possible to color the regions black and white so that no bordering regions are the same color? So we don't want black on black or white on white. Nobody wants to see that stuff, do they? Oh, who wants bricks? Black and white, white and black. Right. Who says this is possible? Straight lines. Only direct. And a few people. Who says this is impossible? What are I asking? Possible or impossible? Possible. Who thinks it's impossible? Okay, so some people think it's possible, nobody thinks it's impossible, and the rest of you don't know. That's right. Can't say for moral reasons. Not because of my arms in the wall. Right. Okay, fine. The people who say that it is impossible are slightly more correct than the people who say it's possible. There is very good reason to suspect that this is impossible. If you look at a map of countries, a little border, then it's definitely not possible to color countries on a map using two colors. In fact, it's not possible using 3, 4, 3, 4. 4 is possible. Why do you know that? Proven by. Okay, there, I wanted to say that. Okay. So it's a 4-color problem. Here, it says you need these 4 colors to color a map, but you can color any map with 4 colors. And this was proven not by mathematicians. Well, the mathematicians helped a little. Apple was built in the 70s. They used computers for the very first time to prove this mathematical theorem. And everybody was outraged. They said, this isn't a real proof. We don't trust the computer. The computer can make a mistake. People did not want to accept computers can prove theorems. But bottom line is the computer did most of the work and it was correct, and now we all accept it and we regularly prove theorems using computers. But bottom line is that you can't color a map, a general map, with 2 colors. It is impossible. So this question is asking for something that is very close to something that is impossible. But the one stipulation that this question has, this puzzle has, that is not in the usual problem, the more general problem, is that here we are dealing with straight lines. And just the fact that there are straight lines means it is actually possible. Oh man, what are you guys going to do if you get this kind of puzzle in an exam? Because you probably can't write this whole essay about the 4 colors theorem. I mean, it will be a different kind of problem, so you won't necessarily know that history. I don't know what to tell you, except that if I ask you something like this, you probably assume that it is possible. I'm not going to ask you if it's something impossible. And the real question is, how do we find the solution? How do we get from the input, which is a lot of straight lines on paper, to the output, which is the coloring of this map? This is the kind of thing we want. We want, you give it a lot of straight lines, and then it needs to be colored like this. This is fine. No black against black. I mean, black next to black. No white next to white. It's all mixed up. Right. Is that a fly? Right. So, how do we go about this? you probably have absolutely no idea. And I probably have no idea either if I just saw this for the first time. In fact, when I did see it for the first time, I thought, I don't think I want to prove this. And I had the luxury of not having had to, so I just went back to sleep. But if somebody tells me use induction, somebody tells you use induction, somebody tells us to use induction, we can get some kind of idea. So the idea of induction is you prove something for a certain number, let's say n. No, let me turn it around. You assume something for a certain number n. You just say it's true. Without any proof, you say, this thing is true if I have n of something. And then you try to prove it for n plus 1. Just one more. Make the problem just one little bit more complex. But for the n plus 1 step, you can use the fact that it's true for n. Even though it's an assumption you make yourself, you can use it in your proof of n plus 1. If we do this, what we can prove is that if it is true for n, then it will also be true for n plus 1. And then all we need to do is to plant a little seed. It's the little button press that will launch the nuclear bomb. All you need to do is to prove it for 0. And if it's true for 0, then we know it's true for 1 because we've proven that it's true for n, it's true for n plus 1. If it's true for 1, we know it's true for 2. If it's true for 2, we know it's true for 3, and so on. So it's true for all n. We can prove something about all n by assuming it's true for n and then proving n plus 1. And the difficult step in induction, apart from the proving, is to decide what am I going to apply the induction to? What am I going to have n of? Do you have any stupid suggestions? This class will work better if I first get all the stupid suggestions and then finally as a climax to get to the real solution. Anybody have any ideas except for the real answer? No. I can think of loads of stuff. Yes. You want to say something? I don't. I can sense it. Yes. Not. Oh. Okay, so what about the following? Guys, you really need to learn to be very imaginative. Learn to use your imagination because most of the time in life you have to bullshit something. And you can't do that if you can't think on the fly. So I really expect all of you to think something. Yes. Margaret.
Lawrence.
Lawrence, that's what
Let's
one off. LM. One little off. Yes, Martin. Lawrence.
Let's end to know the amount of lines that
No, that's wrong. That's the right answer. I want the stupid answer first. Okay. So firstly, what about having n be the number of pieces of paper? I think that's pretty stupid. Because there's only one piece of paper to do. It's not going to help us prove it for 2 pieces of paper. Why is it making noise? Okay, next imaginative answer that I just thought of right now. I'm making this up as I speak. Second, yes. No. Yes, no.
Let n be the amount of unicorns that appear.
Oh, yes, so that's pushing it too far. You say that in the job interview, they'll know you're a brat. And the next thing you know, they'll ask you for more drugs. You're going to drag you in the office. You don't want that job. So, what about n the number of regions? I proved that it works for n regions. All I need to do is prove n plus 1 region. Issue is, I can add a region to this graph by drawing a line across one region, like in the corner here. But I can't split this white region into 2 regions. I can't just add one more white region because the line has to go from one side to the other. And there's no line from one side of the page to the other that'll split off just one little piece of, if I draw the line here to split off this corner, it also splits up there and there and there if I draw that kind of line. And then I haven't got one more region, n plus 1. I've got, I don't know, n plus 4 more regions. Okay, something else. What about, just thinking outside the box. What about if we do induction on the number of colors? I can do it for 0 colors. I know that for a fact. It's not going to touch the paper, it's going to be what it is. I can do it for 1 color. I could, maybe I want to do it for 2 colors. But then it kind of falls flat because I'm not asked to do it for 25 colors. Of course, if the number of colors is more than the number of regions, then it means every region will get a different color. This doesn't feel right to do it for number of colors. Yes. I am. I am explaining it by an example. Okay? We prove something for n, assume something for n, prove it for n plus 1, and we further will see if I put it for 0. That is induction. So, right, let's get to the right answer that some people, Lawrence, yes, have said. We're going to use induction on the number of lines. So, I'm going to prove that we're going to assume that it works if I have n lines, and then if I add the extra line, n plus 1, I'm still going to be able to do it. Okay. Right. So let's just see. Let's look at the seed first. Can I do this for 0 lines? Well, if there are no lines, the whole page has one big region, and I can color that region either black or white, and I would have satisfied the requirements, because if there's only one region, then no 2 regions are white next to white or black next to black. There's only one region. Good. So that's a little seed. So I've got 0. Then I'm going to assume that I can solve it for n lines. So I've got lots of lines, they're on the page, they make the region, or I can color them black and white. And I'm going to ask myself, what happens if I add one more line? So this is induction. I can try to define induction, but I have to use advanced mathematics. I don't understand. So we can define induction mathematically, but it's much easier to work through examples or to explain it in English. I assume for n, and I try to prove for n plus 1. I've got n lines, and the coloring is working fine, but if I add one more line to this, let's call it the graph, can I still do the coloring? Okay, so, sorry, yes?
I'm curious, if you do induction on the number of blocks rather than
Regions. Yes. Yeah, but as I said, it's very difficult to add just one more region. I mean, you can do it in certain places. Let's just go back, because it's sensible. So, let's say it works for, how many regions do I have? I've got 1, 2, 3, 4, 5, 6, 7 black regions, and 1, 2, 3, 4, 5 white regions. So the 12 regions in total. If I wanted to add just one more region, to make it 13, I'll have to draw a line, and it has to be by the rules, which means it goes from side to side. I can draw a line across here. I can't do it on my computer, but I could try to draw a line here, which will cut this black region into 2 regions. I have 13 regions. That's added one more region. And I can draw a line. I guess I can draw a line to cut that region as well, and maybe this region. I can cut all the corner regions into one more region. But I can't cut the middle regions. I can't in any way draw a line that'll cut this white region in half, or in 2 parts, and not any of the other regions. My straight line will go through other regions, and it will add even more regions. So I'll jump from 12 to 17. And that's not what I want. Each induction step is supposed to jump only one unit. So if I work with a number of lines, it's easy to add one more line. I've got this picture, I add some line. Now the coloring is broken. If I have a line running through here, let's just say it runs through here. If I just add the line, I've now broken this white region into two regions, but they're both white. And I've broken this black region into two regions, but they're both black. And this one is broken into two. Let's say that's all. I've broken my color region. I've got three new regions that, by adding one line, I've added three regions. And all three are now consisting of two white parts, two black parts, right next to each other, on either side of the line. So that is not the solution. What I must do is fix this solution, fix this problem. So I really want to draw on here, but I wonder if I can. Let's just see. Let's take pink. Oh, no. Tools. I'm pretty sure I can do this. I thought I could do it before. It doesn't want, I'm sorry. Do I do this? No, not enough time. Right. Okay. So there is a way I can fix this problem. I've just drawn a line. It's divided regions into two parts that are both the same color. So I have to fix the color on one side of the line. So I can just try to flip those colors. But if I flip this white region's top half, then and make it black, then now it's black next to black. So I have to flip this also. And now, if I flip this to white, then it's white against white. So I have to flip that as well. So I have to think carefully if I can do that. But if you think about it, you can do exactly that. You can draw a line here, and just on one side of the line, you flip all the colors. All the whites go to black, all the blacks go to white. On the other side of the line, everything stays the same. Okay. You're getting antsy. I'm not going to waste precious attention. So I'm going to stop here and we'll talk again on Monday. Right. We kind of have to catch up with the other team.